Okay, let's make the previous problem a little bit harder. What I'm going to do is I'm going to take the two masses and I'm going to make them unequal. So we'll have mass 1 and mass 2. I'm also going to take the three springs and I'm going to give them all different force constants, kappa 1, kappa 2, kappa 3. Now, you will set up this problem exactly the same way you set up the previous problem. You'll look at the forces acting on M1. You'll use Newton's second law, force equals mass times acceleration. You'll come up with a differential equation for mass 1. You'll do the same thing for mass 2. You'll end up with two differential equations that will be coupled, both involving x1 and x2. Now the difference here is that the simple coordinate transformation that we did last time using xi, which was the sum and difference of x1 and x2, is not going to decouple these two differential equations. There is a linear combination of x1 and x2 that will decouple them, but it's not as simple as this. So what we're going to look at now is a systematic approach in which you can find that linear combination and determine the normal mode coordinates, the frequencies, and so on. Now, if we look at this problem, the way we would set this up in this normal mode analysis is the first thing we will do is we're going to convert from our displacement coordinates, x1 and x2, into mass-weighted displacement coordinates. So we'll call these q1 and q2. So we'll take each of the displacement coordinates, say x1, we'll multiply times the square root of the corresponding mass that it describes, so m1 here. So the square root of m1 times x1 is q1. So the same thing we do for mass 2, and we end up with these two coordinates, and we're going to go back to our couple differential equations in terms of x1 and x2 and transform them into two couple differential equations with respect to q1 and q2. Okay. Well, so far we haven't done anything but just make that transformation between two mass-weighted coordinates. What we're going to do next is we're going to rewrite these two equations more compactly in terms of a matrix equation. All right. Now, what this is going to allow us to do is to take our coupled equations and express them in the most compact form, which I'm representing by these boldface q double dot, k, and q here. But if you remember how to use your matrices, you'll know that this equation here is present as q1 plus this element times q1 plus this element times q2 equals 0. That gives you this equation. You can get this equation from q2 plus this element times q1 plus this element times q2 equals 0. That gives us that equation. That's how we set up and expand out these matrix equations. But this written as it is now can be more compactly written in terms of these boldface symbols representing the entire set of coupled differential equations. So any coupled harmonic oscillator problem can be written in this very compact matrix notation here, like this. So whether it's two coupled masses with two coupled differential equations or 10 coupled masses with 10 coupled differential equations, we will be able to express them in this very simple form. So this is very powerful. It's very important that you sort of wrap your head around how to write in terms of matrices, because they can save you a lot of space and make the arguments a lot easier to follow. Now, the next important thing about that K matrix is that it's a square matrix and it's a symmetric matrix. So actually, it's a real symmetric square matrix. And so that means that the off-diagonal elements, so across the diagonal, so K12 and K21, those off-diagonal elements are going to be equal to each other when the matrix is symmetric. All right? So what we're going to do then is, with this K matrix, because it's real and symmetric, it turns out that you can always do something called a similarity transformation, where you sandwich it between a matrix called the Eigenvector matrix and its transpose. So I'm going to call this L and L transpose. And that multiplication of L transpose times K times L is going to give you a diagonal matrix. So this transformation requires you to find out what are the elements in this eigenvector matrix that will give you a diagonal matrix when you do this sandwich multiplication here. So these diagonal elements are called the eigenvalues of K, and the columns in this matrix are called the eigenvectors of K. And each eigenvector here corresponds to an eigenvalue here. So in this matrix here, this is the L matrix, the eigenvectors are represented as columns. Here it's the transpose, so the eigenvectors show up as rows. So this transformation will diagonalize our square n by n real symmetric matrix to give us a diagonal matrix. This is a very important property of our K matrix that we will be able to exploit. Now, okay, so summarizing here then, K has eigenvalues. When you diagonalize, it has eigenvalues, lambda 1, 2, 3, all the way down to n along the diagonal. The eigenvectors are in these columns here, and each one corresponds to each one of these eigenvalues over here. Now, I said this L matrix was an orthogonal matrix, so that means that if you take L transpose times L, and you multiply these two matrices together, you will get just the diagonal matrix with just ones along the diagonal. So this is the identity matrix here. So any orthogonal matrix, when you multiply times this transpose, will give you the identity matrix. And whatever the elements are, if we can find the right elements, then the elements of this orthogonal matrix will take K and transform it into a diagonal matrix. All right, so that's a very important property of these real symmetric matrix that we're going to use now. So if we take our differential equation, Q dot plus KQ, and what I'm going to do is I'm going to insert an 1 before K and an after K. So I can always put 1, insert 1 anywhere in any equation, and I'm going to insert the identity matrix in my matrix equation, which is just as valid. And if I do that, I can do that in the form of multiplying L transpose times L. So I'm inserting 1 in front of K and 1 after K by just putting in L transpose times L. And the reason I'm doing that is because I can then regroup these L's so that now I can say that L times K times L transpose, I can identify that as the diagonalized matrix. So the matrix lambda, which is zeros on the off diagonal and just eigenvalues along the diagonal. And that transformation is going to help us decouple the differential equations. So if I take this equation here and I multiply both sides by L, then you can see, well, this side is equal to 0, so there's no problem multiplying that side. We're just still going to get 0. But if I multiply this side times L, then I'm going to have L times Q double dot, and then L times L transpose. Well, that's going to be 1, right? So when I do that, I'm going to have L times Q double dot. The L times L transpose goes away, and I'm just left with lambda matrix here. And then I'm going to be also left with lambda Q. LQ, sorry, here. And so when I write this all out, I'm going to do a redefinition here. I'm going to define that L times lowercase q, I'm going to define as capital case Q. And similarly, L times double dot lowercase q is going to be capital double dot Q here. And this equation here, this matrix equation, Q double dot plus a diagonal matrix times Q, if this matrix is diagonal, then this is going to describe n uncoupled differential equations. So take a stop right there and just take a deep breath and say, oh, wow, okay, you see what we did. We took our coupled differential equations here, inserted 1, we're able to transform this problem in terms of a diagonalized version of K and transform this problem into an equation that has new variables, which these capital Q's are going to be our normal coordinates. So the normal coordinates are linear combinations of the mass-weighted coordinates And the transformation between the normal coordinates and the mass-weighted coordinates is the matrix of eigenvectors that transforms the K matrix into its diagonal form. So these Q's then are the normal coordinates, and they are uncoupled. So if you expand out this set of n coupled equations, n equations, you're going to have n uncoupled differential equations, all of them looking like this here. And of course, once you have this form of your differential equation, we know how to solve this now. We propose a solution, we plug it back in, we get something like this. We make it true for all values by setting lambda equals to omega squared, which means that our normal mode oscillation frequencies will be the square root of the eigenvalues of the K matrix. Put in your initial conditions, and then you have the whole thing written like this. Okay. So we've now written in this very rigorous approach using matrices a very generic way that we can take any coupled harmonic oscillator problem and come up with the normal mode transformation. The only challenge left is to figure out what is that L matrix, what are the eigenvector matrix that will transform K into its diagonal form. So we need to do two things then. We need to figure out what are the eigenvalues and what are the eigenvectors. The whole problem comes down to that problem. So we need to determine the eigenvalues and the eigenvectors of K. Now, it's easy to show that if I take K times one of those eigenvectors, I'm going to get back the eigenvalue times that same eigenvector. Now, if you insert the identity matrix here, I can do that, just inserting 1, and then do a little regrouping, then you see what I get is I bring over K minus lambda times the identity matrix, put all that in parentheses, times the eigenvectors equal to 0. Well, if I use my bold symbols here, down here to represent those matrices compactly, this whole thing is going to look like K matrix minus lambda I times 1, all of that times the eigenvector, the ith eigenvector is equal to 0. So the eigenvalue, the ith eigenvalue, and here's the ith eigenvector. This equation is equal to, this equation here gives us the equation that we can use to solve for the eigenvectors and the eigenvalues. Now, this is an equation that we already saw in this class. This is the same equation we encountered when we needed to diagonalize the moment of inertia tensor to find the principal axis orientation and the principal axis values. So we've already seen this equation. We already know how to work with this equation. So all of that comes back. And so let's take a look then, in this context, how we're going to use this equation. So we know, again, that if we want to get the eigenvalues, we just have to take the determinant, set the determinant equal to 0, and we get an nth order polynomial. We find the n roots. Those n roots are going to be the eigenvalues. Now, in the moment of inertia case, at most we were going to have 3 roots that we had to get. Here, depending on how many masses you have, if you have 100 masses, you're going to have 100 roots. That's going to be a pretty tough problem. So we're going to come up with alternative numerical strategies to get those eigenvalues. But we can do it analytically for small n, just like we did in the moment of inertia tensor case. So we'll do the determinant to get the eigenvalues, and then we'll substitute in each eigenvalues into this expression to get the corresponding eigenvector. But as I said, in the principal axis system of a moment of inertia tensor, the most you had to work with was 3. Here we could have lots and lots of coupled differential equations. So most of the time when you do this, you'll probably be setting this up in a software package like MATLAB, Mathematica, or a Python notebook, and you'll do this numerically, right? You won't be trying to work this out on pen and paper analytically. So like, for example, if you just went to Wolfram Alpha and you said, give me the eigenvalues and eigenvectors of this matrix, and I wrote out the matrix, here it is, written out there, it will give you back the eigenvalues and the corresponding eigenvectors for each. Very, very easy to do it this way, all right? And if you've ever used MATLAB, there's a similar approach. You can get these really quickly. But let's go back to our problem, and let's just keep pushing on this analytically to see what kind of concepts we can get clear in our head here. So our original problem was this. Remember, we had it written out as the lowercase mass-weighted coordinate q double dot plus k times q is equal to 0. So we need to solve this problem, and what we need is the eigenvalues and eigenvectors of k, and from the eigenvalues we'll get the normal mode frequencies, and then from the eigenvectors we'll get the relationship between the mass-weighted coordinates and the normal mode coordinates. Okay. Now, I know I set up a problem that was harder than our original problem, but it turns out that even for this 2x2, working out analytically, that's still going to be a tough problem. So I'm going to go back to our original problem, but we're going to solve it now with this new approach. So if we go back to the problem where M1 is equal to M2 and K1 is equal to K3, or kappa 1 is equal to kappa 3, then what we have to do is take our K matrix. I'll go back to the previous page. We're going to take our K matrix here, and we're going to write it out and as a determinant. We're going to expand the determinant. We're going to get an equation whose roots are going to give us the eigenvalues. So this is straightforward, quadratic. You solve that, and you'll get these two roots for the eigenvalues of that problem. So once we have the eigenvalues, now we can go back and get the eigenvectors. So we'll take the first eigenvalue here, and we plug it into that expression for the matrix. So remember, we're going to go back to this equation here, and we're going to take the first eigenvalue and we're going to plug it into that expression, and we're going to get this expression here. And I'll take this value, plug it in here, plug it in there, expand this out. So I'll take this times that plus that times that. I get an equation. Here it is. That times this times that, plus that times that, and I'll get this equation here. These two equations are actually identical. If you simplify these, they all simplify to L11 is equal to minus L12. So the two elements have the same magnitude, but they're opposite in sign. So that means that the eigenvector associated with this eigenvalue has a form of some number, which we haven't determined yet, but one element is equal and opposite in sign to the other element. Okay, so B is some unknown constant. But just as we did in the moment of inertia diagonalization, we want to make sure that our eigenvectors are normalized. So we also want that L1 squared plus L12 squared, square root is going to give you 1. So if you impose that constraint, then you can find that B will have to be equal to 1 over the square root of 2. So now we have our normalized eigenvector, which comes out to be this vector here with the first element 1 over the square root of 2, the second element here, the L12 is equal to minus 1 over the square root of 2. So we found the eigenvector for this eigenvalue. Okay, that was straightforward. If you do the same thing with the other eigenvalue, you'll get this for the eigenvector that corresponds to it. That's an exercise you can do at home. Now we can take these two eigenvectors and we can construct the full L matrix, putting them together. So this guy here now just goes here, and take the previous result, put it there, and you'll get this matrix here. And that is the matrix that transforms us between the two coordinate systems. So here's the mass-weighted coordinate, here is the normal mode coordinates. And this is written out in matrix form here. All right. So that's it for this section. If we now, in the next video, I'll show you a web app where they simulate these kind of coupled harmonic oscillators for these different cases here. So next thing we'll be looking at after this video example, we'll go into polyatomic molecules, and we'll apply exactly the same approach to figure out the normal mode of polyatomic molecule vibrations.